right, let's go ahead and start with the pink section. So again, you do not have to watch this video in its entirety. If you have just certain questions from certain colors of the review, please make sure that you reference that index that you'll see on the Schoology page, so that way you can access those specific numbers without having to sit and listen to this entire video. But if that's what you choose to do, so be it. Anyhow, let's look at this first one. So it says, assume that you roll a standard number cube, so a 6-sided die, 2 times. What is the probability of rolling an even number in the first die, or in the first roll, and a number less than 3 in the second roll? Okay, so there's a couple things going on here. So first off, we're rolling the die twice. And so on the first one, we want to find what's the probability of getting an even number on that first roll. And then I want to figure out what's the probability of getting a number less than 3 on the second roll. And remember, we want to make sure that we read the vocabulary very carefully. And so I see that we have the word and here. And remember that when in probability, when we see the word and, it means that we're going to multiply those two probabilities. And so let's start with the probability that it's even. So the number, the 6-sided die has 2, 4, and 6 are the 3 sides that are even out of 6 possibilities. So we'd have a 3 over 6, which we want to reduce to 1/2. Now the probability that's going to be less than 3. Well, if it's less than 3, that means it's going to roll and be a number 1 or a number 2. So there's only 2 out of 6 possible numbers that would be a number less than 3. And 2 over 6 reduces to 1/3. And so what we would do is we would multiply these two events. So the probability that it's an even, and, so we use that intersection there, so I'll use that, and a number less than 3, we would multiply, like I said, the two probabilities. So 1/2 times, 1/3 would equal 1/6. So you have a 1 in 6 chance of that happening. Okay, let's look at number 2. Only 93% of the airplane parts being examined pass inspection. What is the probability that the next 5 parts examined will all pass inspection? Okay, so every single one has a 93% chance of passing inspection. And so you want to find the probability that all 3 pass. And so, or I'm sorry, that all 5 parts pass. So there's a couple ways we could look at that. So if you're a visual person, maybe drawing it out would help, or just putting blanks in there just so you can visually see what's going to happen. But we want to find the probability that the first, like if each one of these blanks represent a different part, we want to find the probability that the first one would pass, and the second one, and the third, and the fourth, and the fifth, all of those would pass. And so we'd multiply 0.93, because each one of these have a 0.93 chance of passing. So we would multiply all those together, or we could just think of it this way and say that you'd have 0.93 to the 5th power, because you're going to be repeating that same probability 5 times. And even though the word and is not in there, if you think about it logically, it's not an or situation, so you need to ask yourself, is this and or? Because if it's or, if it's the first one, or the second one, or the third, or the fourth, or the fifth one, only one of them would need to pass if that was the way it was worded. But we want all 5 of them passing. So this would be an and situation, so we would have 0.93 to the 5th power. And when you do that, you get 0.6957 as a decimal. Or if we asked around in the nearest percent, we would say about 70%. All right, so this one, it says you have a drawer with 5 pairs of white socks, 3 pairs of black socks, and 1 pair of red socks. You choose 1 pair of socks at random each morning, starting on Monday. You do not put the socks you choose back in the drawer. Find the probability of each event. Okay, so that's important. Little things like this mean something when we're dealing with probability. So let's look at the first one. It says you select black socks on Monday and white socks on Tuesday. Okay, so now that line that I just highlighted there really doesn't matter, because we're just focusing on, so on Monday, well, I guess it does a little bit. You'll see how. So we have a total of 5 pairs of white socks and 5 pairs of white socks and 3 pairs of black socks and 1 pair of red socks. So there's a total, if I can spell here. So there's a total of 9 socks in the drawer when we start out. Okay, so there's a total of 9 socks in the drawer when we start out. So we want to find the probability that we select black socks on Monday. Okay, so there's 3 pairs of black socks. So we have a 3 in 9 chance of selecting black socks on Monday. But remember, we're not going to put those socks away because we put them, I mean, they're dirty, so we threw them in the dirty laundry. So now there's not 9 socks on the second day to choose from. There's only 8 socks to choose from on the second day. And we want to find the probability that on the second day that we would draw white socks on Tuesday. And so there's 5 pairs of white socks to choose from, so we'd have a 5 in 8 chance of that happening. And so if you multiply those together, 5 times 3 is 15, 9 times 8 is 72. And then we could reduce that and get 5 over 24, because 3 goes into both of those. And that can't reduce any further, so we'll just leave it as 5 and 24. Let's look at part B. Part B, it says you select white socks on Monday and on Tuesday. Okay, so on Monday, we have a 5 in 9 chance of selecting a white sock. Okay, now let's say if we select a white sock on Monday, well, we're not only going to have 8 socks total in our drawer, but also we only have 4 of those being white socks. So we'd have 5 9ths times 4 8ths. And when we multiply those together, we get 20 over 72. And since 4 goes in both of those, this will reduce to 5 over 18ths. Or 5 over 18 would be your answer for that one. All right, let's look at the gold section. So the gold section here, it says the population of a high school is 51% male. Of those who attend a school concert, 45% are male. Are gender and concert attendance dependent or independent events? And we need to explain why. All right, so we know that the probability that there are going to be a male at the high school is a 51%, or 0.51. Now let's read this sentence. It says, of those who attend a school concert, 45% are male. The way that we could interpret that as far as probability speaking is we could say that this is a probability that they're going to be male given that they attend the concert. Because they say of those who attend a school concert, 45% are male. So given that they attend a concert is what we know. Okay, of those who attend a school concert, 45% are male. So that's male given that they are attending the concert, and the 45% chance of that happening. Well, remember, to prove independence, to prove if they're dependent or independent, we have this formula that says the probability of A given B equals the probability of A. So if that's the case, then they are independent. Okay, if probability of A given B equals the probability of A, then they're independent. Well, we have this is the probability of A given B. If this is our A, this is our B, and then that means probability of male would be our probability of A again. And so we're saying that 0.45 here does not equal 0.51. So that means that these are dependent events. So it's important to remember this formula to show whether they're independent or dependent events. Again, if they're equal, they're independent. If they're not equal, they're dependent. All right, let's look at number 2. Number 2, it says the table shows the number of one doctor's patients who caught a cold 1 week and whether or not they exercised regularly. So we see that some people caught a cold and some exercised and some did not. Some did not catch a cold. Again, some exercised and some did not. They don't give us the totals here. It's always good to find the totals. And so if we add 8 and 10, we get 18. 30 and 2 is 32. So that means there's 18 patients that caught a cold, 32 that did not. There's 38 that exercised and 12 that did not exercise. And if you add those together, you get 50. Okay, so if I add 38 plus 12, I get 50. If I add 18 plus 32, I also get 50. All right, so now it says, find the probability they did not exercise given they did not catch a cold. Okay, let's start with the given. So remember, the given amount goes in the denominator. So given they did not catch a cold is 32. That goes in our denominator. So our numerator is going to be the intersection that they did not exercise and they did not catch a cold. So that intersection is 2. So we would have 2 over 32, and we reduce that, and we get 1/16. So we have a 1 in 16 chance of that happening. Part B, find the probability they did not catch a cold given they did not exercise. Okay, so given they did not exercise, that total is 12. And the intersection of they did not exercise and did not catch a cold, again, is 2. So we're going to put 2 in the numerator. So we would have 2 over 12, which reduces to 6th. Okay, so it says, are these two events dependent or independent events? Well, we can use that same formula that we did earlier. So we can find, let's say, the probability they did not exercise, given that they did not catch a cold. Let's abbreviate that, no cold. We want to see, does that equal the probability that they did not exercise? Okay, if they're equal, then they're independent. If they're not equal, then we could say they're dependent. Okay, so we already know the probability that they did not exercise and did not catch a cold. That's what we did in part A. So we have a 1/16th chance of that happening. So let's find the probability now that they did not exercise. Whoops. Okay, so the probability they did not exercise, there were 12 patients that did not exercise out of a total of 50. And if I reduce that, because let's see, 2 goes into both of those, so that would reduce to 6 over 25. That clearly does not equal 1/16th. So these would be dependent events. All right, let's look at the yellow sheet. So it says, what is the difference between a permutation and a combination? Well, a permutation is where order matters, and a combination is where order does not matter. So you just want to make sure you know the difference. Because in a lot of these, you're going to have to determine whether they represent a permutation or a combination. So starting with number 2, it says a basketball coach will choose 5 players from a group of 8 to start the next game. How many different groups of starting players are possible? Well, does it matter the order that he selects them? Okay, it doesn't say anything about that. So the order here does not matter. So this is a combination. And so there's 8 players, and he's going to be choosing 5 of them. You can do that on your calculator, and you get 56 groups. There's 56 different groups that he could create, where he'd be selecting 5 players of the 8. Let's look at number 3. A group of 9 business leaders meets each week. Members take turns being the note taker, the facilitator, and the speaker. And how many different ways can these positions be chosen from the members? Well, here the order does matter, okay, because you have 3 specific tasks. So it's not just 3 that are being selected at random, just do whatever. There's gonna be 3 specific tasks. So this would be a permutation. And again, there's 9 business leaders, and we're going to be selecting 3 of them for these different tasks. It'll be 9 permutation, 9 items, selecting 3 of them. Here we go. And when you do that on your calculator, you end up getting 504 different ways that they can be selected. So 504 would be your answer. Number 4, when randomly choosing 2 coins from a cup of coins that contain a penny, a nickel, a dime, and a quarter, what is the probability of choosing a penny and a nickel? All right, so since we're dealing with a probability, I'm going to set this up as a fraction. Our denominator doesn't care about anything specific. Our denominator just looks at the total. So we have 4 coins, and we're going to be choosing 2 of them. Okay, that's all our denominator worries about. Now, there's a couple different ways we could look at the numerator, but one way would be looking at it this way, is that we would be selecting a penny and a nickel. Now, we have 1 penny, and we'd be choosing 1 of those. And we have 1 nickel, and we'd be choosing 1 of those. And we have 1 dime, but we're not going to choose any of those. And we'd have 1 quarter, and we're not going to choose any of those either. The reason why I like to do it this way is because sometimes we do have trickier problems, and it's important when you have those trickier problems that the ends in the numerator add up to be the ends of the denominator. And it's important that the r's in the numerator add up to the r that we have in the denominator, which is the case here. Now 1 choose 1 is 1, and 1 choose 0 is also 1. So all of that in the numerator just simplifies to be 1. 4 choose 2 is 6, so we'd have a 1 in 6 chance of that happening. So that would be your answer for number 4. So again, the denominator Doesn't care about anything specific. You just look at the totals. So the total number of items they were choosing from and the total number of items out of those that we're going to actually select. So we have 4 coins. We're choosing 2 of them. And the numerator breaks it down into the specific pieces. And in this case, it's in an AND situation. So we would multiply each of those probabilities, which really doesn't matter because they're all ones. All right, let's look at number 5. 3 cards are randomly chosen at the same time from a set numbered from 1 to 7. What is the probability that the chosen cards are numbered 1, 2, and 3? Okay, our denominator, again, doesn't care about anything specific. It just says that there's 7 cards, and we're going to be choosing 3 of them. Now, the probability that's going to be specifically 1 and 3, again, we'd have 1, number 1. So it's very similar. The numerator is very similar to what we had in the previous one, but I'm going to talk too about this one in terms of just common sense. Because there's only one way to select the numbers 1, 2, and 3. So our numerator would just be 1. Or you could look at it that you'd have those individual numbers selected. 1, choose 1, 1, choose 1, 1, choose 1, and 1, choose 0 for the other numbers. But I think it's just easier to do it this way. And so our denominator, 7 choose 3, would be 35. Or if you did it as a decimal, it would be 0.03. So either one of those, depending on, oh, it says round to the nearest hundredths place. So there we go. Got to read those carefully. So we'll just do it as 0.03. Okay, so I'm not going to write all these out. Well, maybe I should. But it says, what are the features of a probability experiment that are necessary for us to consider it as a binomial experiment? All right, I didn't want you to have to sit there and watch me write all that down, so I paused it and wrote those down for you. So you can pause this video now and make sure that you have these correct. But there's 3 different ways, 3 different things to look for: that they have a set number of trials, that they are independent trials, and there are 2 outcomes for each trial. Would be the different features of a probability experiment. You should also take note of the fact that when in our formula, that when we're dealing with these, P represents the probability of a success and Q represents the probability of a failure. And if we know the probability of a success to find the probability of a failure, the Q value, we would just take 1 minus P. So those are some different features of a probability of experiments that are necessary for it to be a binomial probability. All right, let's look at number 2. Here it says a marble is chosen at random from a bag containing 8 marbles, 4 blue, 3 green, and 1 red. Define a probability distribution for this experiment on the sample space blue, green, and red. So what we're going to do is we're just going to find the probability of each of those events. And so let's start with the probability of blue. Maybe I should use blue here. So to find the probability of blue, there's 8 marbles, 4 of which are blue. So we have a 4 in 8 chance of it being a blue marble. Now we want to reduce that. So we would say it's 1/2 or 1 in 2 chance. Now for a green marble, again, there's 8 to pick from, and 3 of those are green. And that can't reduce, so that stays 3/8. And for a red marble, there is only 1 red marble out of the 8 in the bag. And so we have a 1 in 8 chance of selecting a red marble. So these are not uniform, so this would not be a binomial experiment. Let's look at number 3. A light fixture contains 6 light bulbs. With normal use, each bulb has a 0.85 chance of lasting for at least 4 months. What is the theoretical probability that all 6 bulbs will last for 4 months? Round to the nearest whole percent. All right, so there's 6 light bulbs. We want to find the probability that all 6 of them last for 4 months. And you have a 0.85 chance of that happening. Again, so we want all 6 of them to last. And so so that would be the probability of a success, would be your 0.85. The probability of a failure would be 0.15. And we're not going to have any that are so in this scenario, we're not going to have any that are not going to last for 4 months. So we would just type this in your calculator. When you do that, you get 0.3771. Now it says to round to the nearest whole percent. So when we write this as a percent, we move the decimal to the right 2 places. So it would be 37.7%. But we would want to round that to the nearest whole percent. So that would be 38% would be your answer. For number 4, it says there's a 60% chance of rain each of the next 5 days. Find each probability round to the nearest whole percent. All right, so in this case, the probability of a success would be the probability of rain. So that would be 0.6. And then that means that your probability of failure, meaning not raining, would be 0.4. And this is a binomial experiment because we do have two possible outcomes, and these are independent of each other. And every day you have the same probability because it's the same probability each of the next 5 days. So we can use, like I said, we can treat this as a binomial experiment. So it says in part A, we want to find it will rain on at least 3 of the next 5 days. Okay, we're going to have to do a little bit of math here. So it says at least. It doesn't say exactly 3. It says at least 3. So we have to do this more than once. So we would take, so again, 5. So we can start with 3 days of rain. Okay, so at least 3 days. So the lowest would be having 3 days of rain. So 5, choose 3. So with having a probability of a success of rain would be 0.6. So we have 3 days that's going to happen. That means we'd have 2 days because these two exponents, these two exponents have to add up to be n. So that means that there would be 2 days of it not raining. Okay, so we'll get to what that would be here in just a second because we're going to have to do a little bit more work here because we have not just 3 days, but we have at least 3 days. So we could have 5, choose 4, and 5, choose 5. And then we're going to finish that out with these probabilities. So if I have 5, choose 4, so this number and this number, I have students that have asked me, how do you know what number goes with the probability of success? It's always whatever r is because you're treating this as the 5, choose 4, meaning that we would have 4 days of rain. And so we'd want that 4 to be attached to the probability of it raining. So that would be the 0.6. So it means we'd have 1 day without rain. And then lastly, we'd have 0.6. We'd have all 5 days here raining. And then we'd have no days without rain. And so now what we're going to have to do is we're going to have to figure out what each of these are. So we would just type these in your calculators. And when you do that, we would get 0.3056 for this one. This one ends up being 0.2592. And this one's 0.0078. I'm sorry, 0.0778. There we go. And now if you add those all together to get your total, we get 0.6826, which as a percent would be about 68% chance. We'd have a 68% chance of at least 3 of the next 5 days having rain. Okay, let's look at part B. Now, part B, it says it will rain on at least 1 of the next 5 days. Now, we could do this in one of 2 ways. The hard way or an easier way. The hard way is pretty straightforward. Okay, at least 1 of the next 5 days. So we would have 5, choose 1, and then 0.6 to the first power, 0.4 to the fourth power, because we'd have 1 day without 1 day with rain and 4 days without rain. But then we'd have to do that for 5, choose 2, 5, choose 3, 5, choose 4, 5, choose 5, with the rest of the probabilities. I'm not going to write all that out. With all that out, we'd have to do all that. We'd have to plug that all in our calculator. We'd have to add all those numbers together. And that would give you your answer. That's one way to do it. But that's going to take a lot of time. Now remember, we have this idea of a complement, meaning that if we were to add all the probabilities of all the days, meaning getting 0 days of rain, 1 day of rain, 2, 3, 4, all the way up to 5 days of rain, all of those will add up to be 1. Okay, because that would be equivalent to 100%. Okay, so it's going to add up to be 1. So the alternative way to do this same problem would be to instead find out what 5, choose 0 would be. Because that represents that it's not going to rain at all. So rain at least, so that would be 0 days. We would still have that 0.6 to the 0 power and 0.4 then to the 5th power. So that represents 0 days of rain. That means 5 days without rain. And when you do that on your calculator, we end up getting 0.0102. So that means we'd have a 1% chance of it not raining at all. Well, if we have a 1% chance, because again, if we change this to a percent, it would be 1%. If we have a 1% chance of it not raining at all, that means if we subtract that from 100, or if we took 1 minus 0.0102, it's the same idea, we'd get that there's a 99% chance of it raining at least 1 of the next 5 days. Okay, so let me just erase all that. So we could take 1 minus 0.0102. That's the complement. That's everything else. You get 0.9898, which as a percent would be 99%. So the answer for letter B, it's much easier to do it this way using what we call the complement to get your answer, as opposed to actually adding up all of the other numbers together. You just have to remember that the two pieces, the days that's less than one of the next 5 days, which would just be on one option, means 0 days, we would just take and subtract that probability from 1 to get what we're looking for. All right, lastly, letter C. Find the probability it will rain at least one of the next 2 days. So we could use that idea of a complement for this one, or we could add, because this one you'll see that it's pretty easy to do if we do it straightforward, meaning that if we do at least one of the next 2 days, so we would have 2 choose 1 times the probability of rain would be 0.6 to the first power, and then we would have 0.4 to the first power, so we'd have 1 day with rain and 1 day without rain. Again, it says at least, so then we have to go all the way up to of the next 2 days, so that means we'd go up to 2 days of rain. So we'd have 0.6 squared times 0.4 to the 0 power. So you could do it that way. There's only two numbers that you could add. You'd have to add together here if we did it this way, because here you'd get 0.48, here you'd get 0.36. Add those together, you get 0.84, which would be 84%. Okay, so 84% would be your answer. Now the other way to do that is to use a complement, saying that it's not going to rain at all, and then subtract that from 1. Because if you did it that way, again, if it's not going to rain at all, we would get, out of the next 2 days, we get 0.16. Subtract that from 1, you get 0.84. So there's two ways you could do letter C, but this one, it's pretty easy to do it the straightforward way of just adding together these two numbers. All right. Let's look at the blue section now. For number 1 here, it says a tile is drawn from a bag at random and then replaced. The probability of drawing a blue tile is 80%. The probability of drawing a red tile is 20%. What is the expected number of blue tiles in 25 draws? Okay, so this is what we're trying to find. That means that this information about the red tiles, we're not going to need. Okay, so we do know that the probability of success here is that there's an 80% chance of drawing a blue tile. And so that's what we're going to use. Okay, so we're going to have an 80% chance out of 25 draws of getting a blue tile. So all we got to do is take 0.8 times 25. And that'll tell you what you would expect. That's the theoretical probability. What would you expect to have happen in 25 draws? And you would expect then 0.8 times 25 is 20, so we'd expect to get 20 blue tiles. All right, let's look at number 2. It says a 10-sided die has the numbers 0 through 9 on its 10 faces. What is the expected value when rolling a 10-sided die? Is the expected value a possible outcome? Let me explain. All right, so there's two ways that we could approach this problem. I'm going to show you both ways. Let's start with the longer way to approach this problem. And that would be that, so we have a 1 in 10 chance, because there's 10 sides, and each side is equally likely. So you have a 1 in 10 chance of getting each of these rolls. So we have a 1 in 10 chance of getting a 0. We have a 1 in 10 chance of getting a 1. So we're going to do this for all of these. Now, I don't want you to sit and watch all this, so I'm going to pause the video, and I'm going to write all these down, and you can do the same if you want. And then you'll be able to see this all listed out here in just a second. All right, so there we go. So you can see why I didn't want you to have to listen to me or watch me write all that out. So those are all that. So we have, again, 10 sides, numbered 0 through 9. Each of those sides have a 1 in 10 chance of happening. Now, you could type this all on your calculator. Now, if you do that, it's going to be a real pain, but you're going to get your answer, if you do it all correctly, as 4.5. But there's a much faster way to do this same problem, especially on your calculator. And that would be, I'm just going to do it over here, and that would be do it this way, because if you notice, every single one of those has a 1 in 10 chance. They're all equally likely. And you have the numbers 0 through 9. So you could just add the numbers 0 through 9 together. And get 45. And 1/10 of 45 would be 4.5. So I think that's, personally, that's the way that I would do it, because I think that's a lot easier. But either way, you're going to get the same answer for number 2. So number 2, you get 4.5. Now the second part, is the expected value a possible outcome? No, because you're not going to roll and get a 4.5. Okay, so that would be no. All right, let's look at number 3. Now, number 3, it says the probability that a plane will arrive on time from airport A to airport B is 0.625. The probability that the plane is 1 hour late is 0.25. The probability that it's 2 hours late is 0.125. What is the expected number of minutes the plane will be late? Now, the key is the number of minutes the plane is going to be late. And this is, all these numbers are in hours. So we want to make sure that when we're using these numbers that we convert these hours to minutes. So the expected number of minutes, well, let's start with the first one. So the first one would be, technically we don't need to include this, but let's just go ahead and do it. If it's on time, it's going to be 0 minutes late. And that happens 0.625. The probability of that happening is 0.625. And then if it's going to be 1 hour late, well, that's 60 minutes. So it's going to be 60 minutes late, 0.25 of the time, so 25% of the time. And it's going to be 2 hours late, which would be 120 minutes late, 12.5% of the time, or 0.125. And if you plug that in your calculator, now technically 0, you don't have to waste your time doing that because that's just going to be 0. But if you plug the rest of that on your calculator, you get 30 as your answer. So it's going to be 30 minutes, or the expected number of minutes that we'd expect our plane to be late. All right, lastly, let's look at number 4 here. It says, Mr. Minowitz goes to a carnival, when the pandemic is over, of course. He sees a game that he thinks he can win. The game has the following rules. If you roll a number, so you're going to roll a standard number cube, so 6-sided die. If you roll a 1 or 2, you'll lose $2. If you roll a 3 or 4, you'll lose $4. If you win, or if you roll a 5, you win $5, and if you roll a 6, you get $6. So you also win $6 if you roll a 6. Now, the fact that you lose $2 and lose $4, that's significant. So, because when we use these as numbers, we're going to use losing money as a negative number. And positive numbers, or winning as positive numbers. So, -2 and -4 would represent losing $2 and $4. A +5 and a +6 would represent winning $5 or $6. So it says, what is the expected value of the person playing the game? Okay, so it's the person playing the game. What's their expected value? Not the person running the game, how much they're going to earn. So you're going to lose $2 if you get a 1 or a 2. So we have a 2 in 6 chance, or a 1 in 3 chance of us losing $2. Plus, getting a 3 or 4, well, that's also 2 numbers out of 6, which reduces to 1 in 3. So we have a 1 in 3 chance of getting a 3 or 4, and that means we would lose $4. But the probability of rolling a 5, well, that's a 1 in 6 chance of that happening and winning $5. And we have a 1 in 6 chance of us getting a 6 and winning $6. So for the answer for this one, now this one you cannot do like we did the previous one, where we grouped them together and added them all together and then multiplied by the probability. This one, the only way to do it is, or the best way to do it would just be to leave it as it is. And when we do that, you get your answer of -0.1667, which in terms of money, that means that we're losing about 17 cents each time you play. Or you could write it like this, in terms of dollars, but we're losing 17 cents every time we play. So an answer, or to answer part B, when it says, should the person play the game, since your expected winnings is that you would actually, or your expected value for playing the game is that you would lose 17 cents every time you play, it would probably not be a good game to play. So that's how you can figure out if it's a good game or a bad game in terms of the player. Now, in terms of the person running the game, then they're going to profit off of each person. But as a player, it would not be a good game to play.